Feel free to ask any questions while you wait if you'd like. Today's the 22nd. Got another person coming in. Carly, did you get my reply to your text message and email? I know it took a long time, but I want to make sure you got it. Yeah, yeah, you, Carly. No problem. Just making sure you don't miss it. All right. All right. Well, it's about time to start, so I guess I should get started. At some point, make sure you chat me your first and last name so I have it for the roll. You can do it now if you want to. You can do it later, whatever. It doesn't really matter. I usually try to do it about mid-class. That way I can, give full credit to when they've actually been there. But to be honest with you, I really don't take off any points or anything, so it shouldn't matter when you do it, just as long as you do it. Uh, I am gonna let you know there was a little bit of confusion. I had at one time thought the next face-to-face test was going to be after the break. Then I looked on the calendar for the labs that our department handles, and I realized that wasn't a possibility. So I started to scare everybody by letting them know that we actually have it before. Uh, a lot of people really love that. So, anyways, I've got it fixed now. So we're definitely not going to have the next online test until after the break. I've already posted the next practice test for the next online test, which will be due. Uh, Basically, I'm sort of setting it up to be due the day you return or the day before you return from spring break. and it will cover in your class, it'll cover chapters 20, definitely 22, I think maybe 23 as well. The midterm or the next face-to-face class, haven't quite decided on that. I will decide when I make the practice test for that. So just keep that in mind. What we're going on here now is we're jumping into chapter 23, which is on electric, which is on the electric potential. And this is sort of a parallel to how we did chapters 1 through 6. We did Newton's second law, basically. Newton's, oh, actually, it's Newton's three laws of motion. And then chapter 6, of course, was Newton's law of gravity. But all of those, basically, once we got to chapter 3, entailed vectors. And then after we got out of chapter 6, we went and started considering the concept of work and then various types of energy, mechanical energy specifically. So we had potential energy, kinetic energy, that sort of thing. And that allowed us a whole nother way to do the same sort of stuff that we did in chapters 1 through 6, but without vectors. You could still use vectors and you could still get back the vectors, but it took a little bit of work. But the main thing was that you didn't have to use vectors to get a lot of the variables. Therefore, it was a little easier. We're now doing the same thing because in chapter 21, we covered Faraday, or excuse me, Coulomb's law for force, which was the why is this happening every time? Which was the Q1 times Q2 over 4 pi epsilon naught R squared is the equation for force. And of course, the force acts along the line connecting the centers of charge of the two charges. And then we removed that idea that required action at a distance by introducing the concept of a vector field, specifically the electric field, which Coulomb's law gave as Q, the source of the electric field, divided by 4 pi epsilon naught times R squared. And in this case, the electric field pointed along the line connecting the center of charge of Q and the point at which you wish to know the electric field. Okay, so those were all vector quantities, which was, obviously a bit of a struggle because we had to integrate things with cross product. Well, we didn't have to do cross products yet, but we will later. But with dot products and stuff of that sort. Then we covered Gauss's law, which was a way where we could at least solve for the magnitudes of the electric field, but it also had other parts where if you weren't trying to solve for the electric field, you could just calculate, what's the total flux based on the amount of charge enclosed, or you could figure out what the charge enclosed was based on the flux, stuff like that. Well, now we're introducing a scalar thing. So if you think about potential energy as mgh, you can sort of argue analogously with that when you go to talk about electricity. So, for instance, just like when a object like a person or a turtle or whatever ends up on top of a telephone pole, they're at a place of high potential energy. That's because gravity wants to pull them down closer to the center of the earth, and therefore they have this high potential energy. Well, similarly, if you have a positive charge next to a positive charge, positive charge next to a positive charge, then that has a high potential energy because that positive charge wants to run away from that positive charge that it's next to. And it's a little reversed in that in the second case, we're trying to get away from something, but you can also think of it as you're trying to get to the other side, which is less positively charged. So it's sort of like gravity, but that's the main thing. Only the units of potential energy, which are joules, uh, we're going to be compelled to use a different unit and, in fact, a different quantity altogether. And that quantity is the potential, or the electric potential, or the voltage. All of those are synonymous. Okay, so remember the electric potential, the potential, and the voltage are all three words that mean the same thing. Okay, so let's get started by giving you an idea of what that is. So your book starts off by making a similar parallel. And what they start off mentioning was that the change in potential energy, here I go sharing my screen, which would be helpful. I almost forgot again. Waiting, waiting, waiting. So what we learned back, like I said, in chapter probably 7/8, somewhere around there, was that the change in potential energy, and we used U for the potential energy, was, dang it, was equal to the negative of the work done by a conservative force. And in case you can't remember, that conservative force meant that del cross F is identically equal to 0. So that was what that meant. Well, we're now going to basically consider the same thing, but what we find is more important has another parallel. So for instance, we started off with Coulomb's law saying F is equal to Q over 4 pi epsilon naught r squared, where basically you were looking at Q, which had a center of charge, CQ right there, and then maybe you were looking at lowercase q that had a center of charge right there, and this distance from here to here was the R, and the force had to act along that line. So for instance, you could say this is the force on Q due to Q. And you could also say this is the force on Q due to little q. Okay. Well, we did that with force, and that was reasonable. But like I said, we had the problem of action at a distance. So we went a little further and said, okay, let's let something called the electric field be equal to, and I'm going to remind you that there was a limiting process, and the limiting process was as Q approaches 0 of F, the Coulomb force, divided by Q. So by dividing out that lowercase q, we were attempting to take out the part of the force that was due to the lowercase q while leaving the part of the force that was due to the uppercase q, so that ultimately you could just multiply the electric field by the little q to find out the force on Q. Okay, so by dividing by a charge, we found something kind of helpful. And in that case, we basically had this was equal to Q over 4 pi epsilon naught r squared. And I'll just say in the d hat direction, where d hat is just a vector I made up to point in the right direction. Okay. But from a diagram standpoint, it might look a little bit like this. Just as a little bit of a refresher. So there's your x-axis, there's your y-axis, there's your z-axis. Let's say our charge, big Q, is right here. And let's say the center of charge is right there. And in fact, let me make this a little better. So I'm going to say big Q is right there. And let's say the point at which we wish to know the electric field is right there. So what we had to contrive was the idea that the vector electric field would act along the line connecting those points. And in fact, what we'd find is that the electric field would be exactly parallel to that. Okay. So that's ultimately how we did that. Now, guess what? We have a quantity we're going to call, let's say, delta V, and that's going to be basically defined as delta U over some charge Q. So just like we divided out a Q, we're going to divide out a Q again. And of course, that means it's going to be the negative of the work done divided by Q, which can end up looking like the negative integral of F dot dl over Q, which can end up looking like the negative integral of F over Q dotted with dl, which is actually equal to the negative integral of E dot dl. And that's ultimately where we're going. Okay. So this quantity delta V, which is always V final minus V initial, is actually equal to the negative integral from the initial position, let's say R sub I, to the final position, let's say R sub F, of E dot dl, and it is technically a line integral or a path integral. But luckily, uh, when we're dealing with conservative forces, we know one of the cool rules that exists, and we'll cover this a little bit later, is that dealing with conservative fields, you can take a line integral E dot dl for a conservative field E, say, and go from point A to point B or point R sub I to point R sub F. And of course, to do the line integral or the path integral, you have to actually evaluate the integral along the path. But the neat thing is, it turns out that it's independent of path. So the endpoints is really all that matters. So that's going to work in our favor. But right now, we're just more focused on the idea that it is a surface, a path integral, and we got to learn how to make sure we know how to do that. Okay. So in general, there's this quantity delta V, which is defined to be the potential energy per unit charge. And that tells us that the units of V, which also equals the units of delta V, also equals the units of delta V, is equal to the units of delta U divided by the units of Q. And of course, the units of delta U are joules, and the units of charge are coulombs. And we define 1 volt to be defined as 1 joule per coulomb. So this quantity is called the volt, after Alejandro Volta. Now, I did not like the way I wrote that, so okay, so that's the volt. Anybody have any questions about that part? Now, I want to use this to sort of make some points about voltage and how it works. So let's start off with looking at, not unlike what your book does, we're going to look at something called a capacitor, even though your book hasn't even called it a capacitor yet. But you can imagine basically a wire, let's say, connected to a battery. Here's the symbol for a battery. Here's another symbol for a battery. You can either put one long line and one short line, or you can put one long line, short line, one long line, short line again, or you can even do it like 3 times if you really wanted. The main thing is that the long line corresponds to the high voltage end, and the short line corresponds to the low voltage end, like this. And let's say this is 12.0 volts, just for the heck of it. Now, what's going to happen as soon as we connect this wire is the positive side of this battery is going to compel positive charges that exist in the wire. Remember, the wire is a conductor, so it has charges that are free to move. So just by connecting it to the battery, the charges are going to be compelled to move to the left. So we can picture little positive charges. They're all going to move to the left and keep on going this way like this. And ultimately, what happens is you get a number of positive charges loading up on the left-hand plate. Now, those positive charges are going to compel the positive charges in the right-hand plate as well as in the wires to travel this way, so that ultimately the positive charges seem to actually return back to the battery source. But what that causes is a net negative charge to exist on the right hand plate because it scared all the positive charges away. Okay. So now that we have that picture, what I want you to think about is, let's think about this little charge right here, which is going to be a positive charge. And let's say this little charge is in fact at position A. Okay. And what's going to happen is it's going to move on its own accord to over here like this, and that location will be B. What I want you to understand is at position A, the potential energy, notice I use the word energy, that's the key thing here. The potential energy I should say, of the positive charge is high. At B, the potential energy of the positive charge is lower. Okay. So what I'm saying is, over there at A, it has a high potential energy. That's the thing measured in joules. And at B, it has a low potential energy, which again is the same thing as measured in joule and is measured in joules. And what we know is that potential energies drop on their own accord. In other words, particles spontaneously, or things spontaneously, go from high potential energy to low potential energy. Spontaneously, there's that word again that we learned about in thermodynamics. But objects spontaneously go from high potential energy dang it, that's supposed to be a G. High potential energy to low potential energy, so that delta U, which would be in this case UB minus UA, is going to be less than 0. Does that make sense to everyone? That seems just like everyday physics that we've already been doing, right? Okay. So now, if you want to know the voltage, what you realize is that V at A is the potential energy at A divided by the charge. Similarly, the potential or the electric potential or voltage at B is the potential energy at B divided by the charge Q. And I'm saying that that is that charge Q. Now, since the charge is positive, what you see is that delta V, which would be VB minus VA, make sure everybody knows that's it, is actually equal to 1 over Q times UB minus UA, which equals 1 over Q times delta U, and therefore it also is less than 0. Because you're dividing a bigger quantity, UB, minus a smaller quantity, UA, by a positive quantity, Q. And since UB minus UA is negative, then VA minus VB must be negative. Therefore, we reach the conclusion that this spot is higher voltage, and this spot over here is lower voltage. So again, I can say that as the particle went from higher potential to a lower potential. That's another way of saying it. The positive particle went from a high potential to a low potential on its own. The positive particle went from a high electric potential to a low electric potential on its own. That's another way of saying it. And the positive particle went from a high voltage to a low voltage. Okay. Any questions on that? All right. So remember, I made a fuss when we covered Coulomb's law about not inserting the signs of the charge, positive Q and negative Q, into the formula for Coulomb's law. And I even said the same thing for Coulomb's law for the electric field. There are actual instances here where the positive or negative sign actually helps you. And for instance, one of them is when you go to do this quantity, which is delta U is equal to Q times delta V. That is a case where sometimes you actually care about more than the magnitude. And if that's the case, if you care about more than the magnitude, then you need to actually include the sign. So any questions on that? That also brings us to another form of energy, another unit of energy. So let me do that. And it's nice because it's actually a mnemonic all by itself that can help us remember that equation that I just showed you. So if you imagine change in potential energy is equal to charge times a change in voltage, then you could say I could move an electron or a proton, whichever one, it doesn't really matter, 1.602 times 10 to the negative 19th coulombs is the magnitude of the charge of the electron and the magnitude of the charge of the proton. The main thing is what I'm trying to do is use that amount of charge and consider how much energy would be actually created if that charge was to traverse a voltage difference of 1 volt. So that's what we're working on here. And in fact, you can see that this turns out to be 1.602 times 10 to the negative 19th. Let me rewrite that. I don't like how that turned out. Times 10 to the negative 19th joules. And what I'm going to tell you is this quantity is defined to be 1 EV. See how that E looks like the symbol we use for the charge of the electron? And see how the capital V looks like the sign that the symbol that we use for voltage? So it's actually got the built-in formula as its symbol. This is called the electron volt. Okay, and 1 electron volt is equal to 1.602 times 10 to the negative 19th joules. Okay, so that's a nice unit. It's a good unit whenever we're dealing with atoms, electrons, protons, neutrons, molecules, those things at the microscopic level. It's very good to use in that situation. So just remember that it comes in really handy. Like for instance, whenever you guys do your labs, if you haven't done it already, the magnetic deflection lab, we actually used a voltage. So magnetic deflection lab, we use, let's say, 3,500 volts to accelerate electrons. And one of the symbols that we use for electrons is that little lowercase e that we use for the electron charge. And we just put a superscript of a negative on it and then an apostrophe with an S on it if we want to refer to more than one of them. That 3,500 volts makes it very, very easy for us to calculate the kinetic energy of the electron after it goes through that voltage difference. In fact, delta K is equal to delta U, which in fact, in this case, would be 3,500 electron volts. Isn't that nice? I don't have to do any math. All I have to do is just take the 3,500 volts, and since I'm dealing with electrons or any other thing that has uh, the same charge, at least in magnitude, as the electron or proton, it's just put an EV after it and you're done. Any questions on that one? All right, so there's the introduction to the new unit. I just wanted to go ahead and knock that out of the way. What I want to do now is consider an example just to make sure we all understand what's going on. Your book gives this particular equation, and it's sort of the same thing I wrote. All this stuff right here, probably of all of it that I wrote, that's probably the most important of the equations. However, all the stuff at the top is important as well. So your book goes on to say, crap. Your book goes on to say that VBA, which is supposed to be equal to delta V, which is supposed to be the voltage B minus the voltage at A, is actually equal to the potential energy at B minus the potential energy at A divided by the charge Q, which is actually equal to the negative of the work done in going from A to B over the charge Q. So this is another version of the equation that I just wrote myself, but this is the one the book has given you. They call it equation 23. I got to start picking my pencil up better. They're calling it equation 23-2b. Okay, so that's one that really comes in handy. Uh, I think we've all seen now that the volt, of course, is also defined to be 1 joule per 1 coulomb. So if you ever need to break that down, we can. But let's look at an example. So your book has a pretty decent conceptual example, and it's conceptual example 23.1. It says this is about a negative charge. Suppose a negative charge, such as an electron, is placed near the negative plate in that figure that I just drew. So it's literally the same picture I just drew, but it's a slightly different one because they took the time to put a negative charge next to the negative plate instead of just the positive charge next to the positive plate. I'll draw it in a second, but suppose a negative charge, such as an electron, is placed near the negative plate in that figure. If the electron is free to move, will its electrical potential energy increase or decrease? That's the big question. So I'm going to draw another line to separate this. And now let's look at our plate. I'm going to say this is our plate. It's got a positive charge here, 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 and here. And then it's got a negative plate over here that's got negative charges like this. And what we're wanting to do is place a negative charge right here. This has a charge of negative Q. And this would be we're going to call this still position B, and this over here is still position A. And what they're asking is, if the electron is free to move, will its electric potential energy increase or decrease? So if the, and by the way, I'm going to say it's that, if the electron is free to move, oops, will its electric potential energy increase or decrease? So first off, I want to ask all you. So I really want all of you to think about it. You don't have to blurt the answer out, but you're welcome to if you want. But I want to give everybody a little bit of time so that they can actually think about the answer themselves. But the question is this: is this question asking about voltage measured in volts, or is it asking about energy measured in joules? This is a big key to getting questions right in this whole chapter and future chapters. Anyone? And you can chat it too. I've got the chat window open now finally. I had it open earlier, but when I share screen, it disappears. Anyone know? All right, now I'm not getting anybody necessarily replying to this, so I'll ask it again just in case someone doesn't understand. It says, if the electron is free to move, will its electric potential energy increase or decrease? And my question is, are they asking about the voltage, or are they asking about the potential energy? If they're asking about the voltage, they're talking about things measured in volts. But if they're asking about the potential energy, then they're talking about things measured in joules. So when they say, will its electric potential energy increase or decrease? Which one is it asking about?
Potential energy.
Go ahead, Darnisha. You actually did answer the other part of the question, right? Where you said it was decrease. That's good. But is it the potential energy, or is it
Potential energy
very
will
good?
decrease.
Very good. That's exactly right. So the big thing here is, yes, the word energy is sort of the thing that should point you guys to the right answer. If they say potential, that could go either way, but once they say energy, it has to be potential energy measured in joules. So long as there's using the word energy, you gotta say joules. And yes, we did learn, as I wrote in this paragraph down here, objects spontaneously go from high potential energy to low potential energy. And I think you can see that the negative charge being next to the negative plate is a high potential energy. Think about high potential energies being uncomfortable. So I'm going to say this is a high potential energy for the electron because it is not comfortable. So that's one way of thinking about it is if it's uncomfortable, meaning like if you were at the top of a telephone pole, you'd be uncomfortable because it's kind of scary, you could fall. Well, the same thing here. The electron's not comfortable because if it had its way, if it had its ruthers, as some people say, it would be compelled to move over to the other side. And that's in fact exactly what it would do, is it would move over to here and things only move in a direction of decreasing potential energy. So that means the potential energy of the electron here is low at A. Does that make sense to everyone? So we've answered the question, which is will its electric potential energy increase or decrease? This means the electric potential energy will decrease, as a couple of my students were good enough to write in the notes and stuff like that. So we've got that answer. Everybody follow that? But I want to follow that up with what will happen to the voltage. In other words, what's going to happen to the electric potential as opposed to electric potential energy? So answer this is B a point of high, oh no, whoa, that darn it, or low electric potential. So is B a point of high or low electric potential? Anyone? Brandon says low, and he's absolutely right. Okay. So would you say the point A is high or low? And Brandon says high again, and he's right again. Okay. And in fact, you can tell that because what you can say is we can do delta V. Well, actually, let's just start off with the voltages. One more. Okay. So V at A is equal to U at A divided by negative E, which is the charge of the electron, which implies that VA is negative. Let's say VA. Actually, I don't want to say negative necessarily. I will say VA is, we said A was low potential, so it is a low and negative. And then we'd say VB, which is equal to UB over negative E. That is, since the B was actually a high potential, this is and these two combined tell us that VB, which is or excuse me, VA minus VB, which is, of course, final minus initial, is actually going to be a high negative number minus a low negative number. So you could say it'd be something along the lines of -7 minus -3, which tells us that in fact VA minus VB is less, and actually I should stick to red on that one. It's actually less than 0. Now that's a big deal. This tells us that negative particles go to delta V less than 0. In other words, negative particles travel from the negative side of a battery, say, to the positive side. And we actually know now, Ben Franklin, of course, was the one that gave us the idea of using positive and negative charges to separate like electrons from protons, even though we didn't necessarily have them then. But the main thing is he came up with the idea of using those signs, and he had a 50-50 chance at choosing what was going on. Ultimately, he chose incorrectly, so that we have this idea that positive charges leave the positive side of the battery and go around the circuit and return to the negative side, when in fact the exact opposite happens. The negative side of the battery compels the free electrons to move around the circuit the opposite direction and go back towards the positive. The good news is there's exactly one experiment that you can do, or one sort of setup that you can make where it makes a difference, and that's called the Hall effect. So we don't have to worry about it. We can still pretend like positive charges leave the positive terminal and enter the negative terminal. And unless you're examining the Hall effect, which is where you submerge those wires in a magnetic field, then you're not going to really have to worry about it too much. Okay, so you don't really have to worry about what we call conventional current, which is the direction positive charges would flow, versus actual current, which is the direction negative charges flow, because there's really no problems with it. Anybody have any questions with that? So some rules we figured out is that positive charges go from high potential energy to low potential energy. Negative charges go from high potential energy to negative to low potential energy. So they're both the same in that sense. But positive charges go from high electric potential to low electric potential, where negative charges go from low electric potential to high electric potential. So just keep that in mind, and you should be good to go. In fact, I hardly ever, even though I told you you can use the sign in that equation, delta U equals Q delta V, I hardly ever use it because I rather work out the details of what a positive charge and negative charge does to work it out as opposed to just trusting my sign. Okay. So it is sort of helpful. Anybody have any questions on that? Now, your book does give you some useful voltages and stuff like that. So I'm going to stop and share my screen with you on that real quick, just so we'll have some common background as to voltages in general. So what you're looking at right now is some typical potential differences or potential or voltages basically. And what they're saying here is that basically the difference in voltage from, say, a cloud to the ground. So you could literally imagine taking the black terminal of your voltmeter and either sticking that in the ground or holding it up to, with a really long wire, holding it up to the area of the actual cloud, and then taking the other end and doing the opposite with it. So black, you can see the black terminals plugged into the ground, the red terminals held up at the actual height of the cloud. And when you did that, if you had a significantly larger and better voltmeter, you would find that that voltage difference for a thundercloud is on the order of 100 million volts. That's a huge voltage. In fact, the breakdown voltage for air is about 3 million volts per meter. That's actually not really the breakdown voltage, even though it says volts per meter. It's actually the breakdown electric field. It turns out when the electric field is so strong that it gets up to 3 million volts per meter, then 3 million volts is enough for the air to become ionized over a whole meter, and lightning will strike over a meter distance. Okay. That also means that if you come to within a millimeter, which of course is 1/1000th of a meter, then you can divide the 3 million by 1,000. You'd say, oh, to span a distance of 1 millimeter, I'd need 3,000 volts. And that's more or less what's going on with the spark between your hand and a doorknob during the winter, for instance. You can also see high voltage power lines. That's those towers that I told you that sort of look like people without arms and without heads. They've got shoulders and they sort of have a deltoid and maybe even the tops of their biceps and triceps, but they don't really have anything going any further down than that. And they definitely don't have a head. And you see them running through, columns of trees out in the country and over mountains and stuff like that. Those are the high power, or they also call them high tension lines. Those guys are 100,000 to a million volts. And we'll learn later that the reason they do it at such a high voltage is to save a butt ton of money. Okay. The automobile ignition, even though the battery of a car is like 12 volts, the ignitions usually runs on the order of 10,000 volts or more. Okay. Automobile battery, it said 12 volts. The household outlet, so those receptacles, for instance, that you're used to looking at that look something like this, you can imagine there's sort of a circle, and then they have a long slot and a short slot, and I'm trying to remember. Yeah, I did do it right. The long slot's on the left and the short slot's on the right. What I'll tell you is this little guy right here is ground. So a lot of, at least the old timers, uh, will wire a house and they'll make the receptacles upside down, which I would say is a little bit safer. Okay. The reason being is if you actually have, let's say this is the side of the receptacle, there's your receptacle plate, say like that. If you have a plug, occasionally what happens is the actual plug will be pulled a little bit out like this, and then the wire comes off this way. If it's rigged this way, then this little
Pastor, can you share
part.
your screen?
Oh, yeah, yeah. Thank you. I completely forgot about doing that. Yes. Let me kill that real quick because this is kind of important and something that I definitely want you guys to understand. There it is. Okay. So I'm drawing this now, and you'll see what comes up. Hopefully. Still waiting. Still waiting. It's coming any second now. Okay, so you see those are the two receptacles. One is wired probably the way you see most of the time with the blue one. The purple one is the way you probably don't see it wired too often, but I actually prefer. And the reason being is notice that ground is at the top. So when the plug becomes unplugged, like it is here on the right-hand side, if a kid were to walk by, with a toy sword or a piece of metal or something like that and swing down in the vicinity of that receptacle, they could actually hit this part right here. If that part's the ground, then no big deal. But if that part is one of the two hot wires, then yeah, it could really hurt somebody. So yeah, I think it's a little better to do it this way because the ground's on top, and you things tend to fall downward as opposed to upward. So if it was the other way around, then it came out, it wouldn't be a big deal, right? Uh, if it's with the actual ground on top, it's not a big deal. But when the ground is on the top, or excuse me, when the ground is on the bottom, then something falling downward, landing on top of the plug, is going to hit one of the live wires, and that's a problem. So what you'll actually discover is one of these wires, one of the rectangular slots, is a black wire, and that's generally hot, and then the other one's a white wire, and that's generally neutral, and it's sort of like a return path for the current. So if you were to hit the neutral, unless something's going on somewhere down the line on that same circuit with the neutral, then the neutral won't hurt you. And sometimes they are doing stuff appropriately on the neutral line, so it could hurt you. But the main thing is the black one you definitely don't want to touch, and the white one I wouldn't touch either, just for good measure. So that's what the household voltage is. In the manual, the book actually said that this is on the order of 10 to the 2 volts. In fact, typical household is what we call 120 volts AC. And what that means is basically if you made a plot of the voltage, it would look like this and would bounce back and forth by about, let me double check my numbers. I think it's like 145, but I want to double check. Let's see, 120 times the square root of 2. Yeah, it's about 170. So it bounces back and forth between 170 and negative 170. And the value 120 that we use is called the root mean square. And the VRMS, root mean square, is on the order of 120 to 125 volts. Okay. The table goes on. It talks about flashlight batteries. So, for instance, AA, AAA, C batteries, D batteries, those are all 1.5 volts. Of course, the 9-volt batteries, the rectangular ones that you put in your smoke detector, are 9 volts. You can buy those dry cell batteries that are a little bigger. They come in like 6 volts and 9 volt and 12 volts and stuff like that. Uh, your book does mention the resting potential across a nerve membrane is on the order of 10 to the negative 1 volt, so 0.1 volts, and the potential changes on the skin due to a ECG, which is another way of saying an EKG, or an EEG, which is an electroencephalograph, is 10 to the negative 4th volt. So you're literally detecting 1/10,000th of a volt in that case. Any questions on that? All right, and like I said, we'll get more in terms of we'll talk more about electricity of a house and that sort of stuff. We will get into AC. I'll tell you how to deal with AC circuits. I'll tell you uh, how they're wired, how they're sent to us, how we differ from Great Britain, stuff of that sort. But that'll be later. Uh, right now, what I want to do is we have another problem. I'm going to say, suppose an electron is accelerated from rest through a potential difference of 5,000 volts. So an electron, oh man, I hate it when it does this. Stop that, all that, go away. Okay. An electron, so this is sort of like the magnetic deflections lab. So an electron is accelerated through. Let's go ahead and work, for instance, with some of the voltages that we did in the actual magnetic deflection. Let's say through a potential difference of VB minus VA is equal to VBA, which is equal to delta V, and I'm going to say that's 3,500 volts. What we want to know is A, what is the change in the electric potential energy of the electron? So what is delta U for the electron? B, what is the kinetic energy? What, dang it. The change in kinetic energy. And then C, what is the speed of the electron? So notice the terminology I'm using. I just used the word, the symbol E minus to represent an electron. Okay, so first off, we want to know what is the change in potential energy. So what we do know, here's our solution. What we do know is the equation that, remember I said we can use the symbol for the electron volt to remind us the formula. And the formula is delta U is equal to Q delta V. And remember the symbol for the electron volt is that, and notice that looks just like Q times V. So again, that's why I'm telling you this. That's why I'm giving you this as a mnemonic. So if we want to do part A, we're going to say delta U is equal to 1.602 times 10 to the negative 19th. So this is again a case where you're seeing me not include the sign, because all I care about is the magnitude. We just want to find out what is the change in potential energy. In fact, I know it's going to be a negative change in potential energy because that's what electrons do, is they naturally go from, or excuse me, it's going to be a positive change in, it'll be a negative change in potential energy, but a positive change in voltage. So that's what all particles do, is they all automatically decrease their potential energy. So I'm just looking for the magnitude right now, but I'm going to say it's this times 3,500 volts. And of course, when I multiply that, I do 3,500 times 1.602 e to the negative 19. And that gives me 5.607 times 10 to the negative 16 joules. And technically, I was using the magnitude of that. In reality, we all know that, dang it. In reality, we all know that delta U would actually have to be negative. So if I'd used the negative sign in there, it would automatically came out right. But like I said, the main reason is I wanted you to think about it each time you do it so you don't make any careless mistakes. Anybody have any questions on that one? Okay. So part B wants to know what's the change in kinetic energy. One of the versions of conservation of energy that your book gave, I didn't use it. If those of you have me for 241, I chose not to use that, but you can. So I'm going to use it now, and that is delta U plus delta K is equal to 0. That's one version of conservation of energy. But from that one version, we can say that delta K is equal to the negative of delta U, which obviously is going to be a positive 5.607 times 10 to the negative 16 joules. So that's our answer for part B, where it asks for what is the change in kinetic energy. Now for part C, they want to know what is the speed. So for part C, what we know is delta K is equal to 1/2 m v final squared minus v initial squared. We're going to assume the particles started off with a velocity of 0. So this is going to give us 1/2 mass of the electron times, times V final squared, so that V final for the electron is actually equal to 2 times delta K over M, and then we got to take the square root of all that, so that's going to be equal to the square root of 2 times 5.607 times 10 to the negative 16th joules. No, I don't need that many sig figs. I just keeping it because I already have it. Now, here's the part your book did actually, when they worked an example like this, they did actually give you the mass of the electron. Of course, you know how my tests go now. I have the front covers of the book in your test, so you can automatically look up the mass of the electron, and that also alleviates my need to have to tell you. So it relies on you knowing a little bit more stuff. So I'm going to divide this by 9.109 times 10 to the negative 31st kilograms, because that is the mass of an electron. So I'm going to take this 5.607 times 10 to the negative 16. I'm going to multiply that by 2. And that's a very, very small number. Now I'm going to divide that by a way smaller number, which is 9.109 e to the negative 31. And that gives me a really huge number. Now I'm going to take the square root of that number. By the way, the numbers like 12310910306400026. So that's all one number, not even to the decimal place. So I'm going to take the square root of that now, and I get 3.51 times 10 to the 1, 2, 3, 4, 5, 6, 7th meters per second, which is still more than a tenth of the speed of light. So we really shouldn't have done it with classical physics with 1/2 mv squared. There's a whole different formula you're supposed to use when things are comparable to the speed of light. So anyways, that does do it. So that's how fast, in some sense, the electrons were going that we sent in the magnetic deflections lab when we used the voltage of 3,500 volts. Pretty cool, huh? Anybody have any questions on that one? All right, and what that looked like, by the way, I just want to draw this picture for you. What we had was like a little electron gun. You can sort of picture as like a barrel of a gun or something like that, and out popped little electrons. Okay, that little electron would be moving this way, and the reason it moved this way is this side over here had a net negative charge on it. And then over at the other side, we had a plate that had a net positive charge on it, like so. And the positive charge is uniformly distributed. So basically, there's no part of the plate that's more compelling to catch the electron than any other part. So they just wisely put a little hole right in the center, and the electron just automatically goes right through that hole like that. Okay. And in fact, if you took your multimeter, and your multimeter, of course, has a red V omega port, and it also has a black COM port like this, what you would do is connect the black COM port to this, and the red V omega port you would connect to this plate right here. And what you'd see is this thing would read 3,500 volts. Does that make sense to everyone? So this is actually a real picture, obviously a drawing, of course, but I mean, it's a real picture of the direction that an electron tends to go in a voltage situation. So hopefully that helps you. Anybody have any questions on that? All right, so now I can start using the integral form of Gauss's law, or excuse me, of the definition of voltage. So for instance, what we can imagine is, let's draw our capacitor that I told you about earlier. And let's say the capacitor is oriented like this. Okay. And let's say in this case, we're going to actually allow the positive charge to move uh, the way we're going, the way we were planning on moving. And what I want to do is calculate the actual difference in voltage from this and use it to determine how the difference in voltage is related to the electric field. So we learned when we did the E-fields lab that for a parallel plate capacitor, essentially the electric fields were uniform. So you would have basically a electric field line like this, and they were all parallel, and technically you'd space them equidistant apart to show that they were uniform, because if you had one area where the lines were closer together than another area, that would suggest the electric field wasn't uniform. And in fact, what we found was the electric field sort of bulged out a little bit at the edges, but in the middle, the electric field was uniform. What I'm going to do is now draw a coordinate system right here like this. That's going to be my x-axis. That's going to be my y-axis. And this little spot right here is going to be a distance d. Okay, so in other words, that would be marked d centimeters or d meters on the x-axis. Okay, what I want to do is use delta v equals v final minus v initial equals negative integral from the initial to the final of E dot dl to find how, whoa, how delta v is related to E. Okay, that's what we're looking for. So what I know here is the electric field is a constant. So I'm going to say solution E is equal to a constant and that is multiplied by a unit vector that points to the right, and that unit vector, of course, we can see is I hat, right? And that is mainly true because we're staying away from the edges of the actual capacitor. Does that make sense to everyone? Staying away from the edges, so the electric field is fairly uniform. We're going to actually carry out our integral along this path which I'll draw as green right here. Okay. Okay, in this particular case, it doesn't matter too terribly much, but there's a rule that you have to pay attention to when you're doing line or path integrals like this. One thing is that you actually have to take the integrand and make sure it's evaluated along the path. So for instance, if you were integrating along the path y equals x squared, you'd take your electric field if it was a function of x and y, everywhere you see y, you replace it with x squared. And that would actually nail down the electric field to the part along the path. Another thing you got to do is you actually have to use either the DL or the range of integration to dictate which direction you're going. You can't do both. Okay. Uh, Sometimes you can by default, and that means that it's okay. It's not a big deal. But the general rule is one of them, DL, say, points in the direction that you're actually integrating, and then the other one just goes in the positive coordinate direction. Or alternatively, the range of integration points the direction you're going. It's pretty cat. And then the DL points in the positive coordinate direction. That's the main thing. So that's what we're going to try to do. So I'm going to say the solution is delta V is equal to the negative integral of E dot DL. Now I'm going to keep the negative and I'm going to put in E as E times I hat. And then, of course, it's got a dot product with it. And the DL is supposed to be a differential line segment parallel to the path. Okay. This path is parallel to the x-axis. So I'm going to call the DL just plain DX. And here's where I choose, do I want to dictate the direction I'm going by using the differential line element, or do I want to indicate it in the range of integration? I am going to, for this particular instance, indicate it with the DL. So what I'm going to say is indicates direction of integration. And this will just go from low coordinate to high coordinate. So that's the rule. You do from low to high in one, and the other one you do the actual direction. As you can tell, in this case, it doesn't matter because they're both the same thing, right? We're going from x equals 0 to x equals d, which happens to be the same direction as dx times I hat. So in this case, it really doesn't matter too terribly much. What we're going to do is say this is equal to negative. The e is a constant, so I can just pull it out in front, and then I'm going to say the integral from 0 to d of make sure I got everything right. I want to make sure the signs and everything are working out right. So I'm integrating from x equals 0 to x equals d. I'm saying the electric field points to the right, which is from the positive to the negative, so that's right. And oh, yeah, I should come out with a negative change in voltage here because I'm going from high voltage to low voltage. Now, what I have left is a dx and then an I hat dot I hat, but you guys are all brilliant now. Y'all have had many experiences with this sort of thing. So can someone tell me what I hat dot I hat is? And let me turn on the chat. Looks like somebody might have answered it there. One. Everybody, anybody not remember what the I hat dot I hat is? Very good. Brandon says it's 1. And it's 1 because remember that it's the magnitude of one of the vectors times the magnitude of the other vector times the cosine of the angle between them. These two vectors are identical in their unit vectors, so both of them have a magnitude of 1. So it'd be 1 times the cosine between them. But the vectors are identical, so the angle between them is 0, and the cosine of 0 is also 1. So I get 1 times 1 times 1 equals 1. And ultimately, what this gives me is just negative E times D. Now, notice I did integrate from left to right. So I went from the voltage being high to the voltage being low. That's why the negative's there. But that's actually the result. So for a constant uniform electric field, delta V calculated along a parallel path or anti-parallel yields delta V is equal to plus or minus E times D, where D is the distance. So that's the only time that's really valid. I've seen people put this in for all sorts of things. E times D is the voltage. Okay, that only works if you're integrating either parallel to or anti-parallel to the field lines, and the field is uniform and constant. Okay, but in that case, it is that. So that brings me to one question. We've only got about 2 minutes left, 3 minutes left. What we'd like to know is two parallel plates are charged to a potential difference of 5,000, or excuse me, of 50 volts. So what we have here is a plate, the voltmeter saying 50 volts, like this, okay? And we're going to say the distance between these two plates, D, is equal to 0.050 meters. And what I want to know is, what is E? And specifically, I really want to know the magnitude of E. Okay, the main reason I'm doing this is I'm showing you a brand new unit of the electric field. We've been using the unit of the electric field as newtons per coulomb. I'm going to give you a much better unit. So here's our solution. I just wrote that sentence. That sentence shows us that delta V is equal to E times D. Therefore, E is equal to delta V over D. So E in this case is delta V over D, which equals 50 volts divided by 0.050. And I'm assuming that 50 volts has 2 sig figs. That's why I just put that decimal there. Okay. Now, that's 50 divided by 5/100ths. So basically what we're going to do is take the 50 and multiply it by 100. That's going to give us 5,000. And then now I'm just dividing it by 5.0 meters, because that multiplying by 100 took care of the decimal place being down there. So ultimately we get 1,000 volts per meter. So that's our new unit of the electric field, by the way. It's a volt per meter, not necessarily just a newton per coulomb. So that's the main reason I wanted to work that. The units for the electric field are newtons per coulomb, but now they're also volts per meter. And that's it. We will solve more problems next week, but you guys are free to go. And I'll wait here for the last person to leave. If anybody has any questions, make sure you do send me a chat of your first and last name so I have you on the roll. But other than that, you're free to go. And yes, I did push the final back, so or the second face-to-face test back. You're welcome. It will be after spring break. So it'll be the lab immediately after spring break. Whatever day that is for you guys. I think you guys do it on Tuesday, don't you? Yeah. So it'll be Tuesday. Well, thanks for coming, everyone. I hear some speakers clicking, so I'm thinking someone's trying to talk or something, maybe.
I had a question about
Hey,
the
Shayla,
lab.
how you doing?
Good, how are you?
All right. Let me kill the recording because I know this part's not necessary. I'm going to do stop share real quick, and I'll stop recording for you.